Hello, thank you. Perfect. I just want to make sure my sound is on here and so I can see. The raising the hand thing's been working pretty well when I see it, and the chat works really well, but I wanted to make sure the sound was going as well. Okay, so welcome back to Chemistry 2342, Organic Chemistry 2 on our summer session here. We're rallying through our last 2 weeks of class. We're going to finish up chapter 19 today. And then tomorrow at the beginning, before our activity, I'm going to do a compare and contrast all these reactions involving enolates. Okay, so we can, and that's going to be partly the table I sent out today, and partly the table that I'm gathering together today, the compare and contrast between the aldol and the conjugate addition and a Michael reaction, which we'll learn today, and how they're all they all seem like they're very complicated. So I want to simplify the idea of the certain things do certain reactions. They all have the same mechanisms because we all make the enolate and we use them to do other things. But so we need to start recognizing that how the skeletal structure of our compound changes with each of these reactions. So what you should have received today by email is a PDF file of this kind of summation of chapter 18 reactions and what to look for in the changing of the functional group and the changing in the number of carbons, which I call the skeletal structure of our material. Okay, so for administration for today, of course, we have class this week and next week. We're only covering 2 chapters next week. They are both very short. I should get through both of them on Monday. And so if we get through both of them on Monday, that gives us 2 days to start our review for our exam. Okay, so and our exam is, of course, on Thursday, not at the regularly scheduled time. So please mark that out on your calendar. Okay, homework for Top Hat is due on Thursday at midnight, and then it's free to review for the exam. Our third Zoom project will be talking about these structural changes and specifically the different reactions we're going to talk about, we're going to finish up today, plus all the ones that form rings. We actually are going to end up with 3 different reactions that form these rings. We're going to have the Dieckmann reaction, we're going to have the intramolecular aldol reaction, and we're going to learn a new one today called the Robinson annulation. Okay, so there's going to be a little exercise with those 3 of the ring forming ones and a couple of the other kind of a fill in the table to figure out the functional group transformation and skeletal changes with the different reactions from chapters 18 and 19. Okay. Again, our exam is Friday over chapters 18 and 19 only. It begins at 12 o'clock unless you've made other arrangements with me. Okay, so if there are any questions about administration, I'll answer those now. And if not, I'm going to go ahead and start to share my screen and get moving on the rest of chapter 19. Okay. So when we ended yesterday, we talked about that aldol condensation. And the aldol condensation is specifically for aldehydes and ketones. And because it's specifically for aldehydes and ketones and we get the addition at that alpha carbon, we end up typically with either a carbonyl of some sort and an alcohol in that beta position. Okay. Now, when we have that alcohol in the beta position, if we don't heat it, we can actually isolate that compound as the beta hydroxyaldehyde or beta hydroxyketone. Okay, so at that point, that's just the aldol addition. Okay, so all we've done is add something to the enolate. We've added the enolate of one to the carbonyl of a different one, giving us that product there, that alpha hydroxyaldehyde. Okay, now if you take that compound, acidify it, and heat it such that it loses water to generate an alkene, that's when it converts from the aldol addition to the aldol condensation. Okay, so and many times what they'll do is just have the number 1 reaction is an aldehyde with base, and then step 2 is acid and heat. And so what they're asking you to do when you see that is you're already going past the aldol addition and you're going to dehydrate that. And when you dehydrate that, you get a conjugated carbonyl and alkene. Okay, so and they conjugate that way because it is more stable to have your conjugated system. So that you are going to dehydrate to give you the conjugated, more conjugated system. Okay, so to review the aldol condensation, our aldol addition, our first step is to deprotonate one of these alpha hydrogens here on an aldehyde or ketone. We're using an aldehyde here. Now, so if one of these is deprotonated as the enolate, it can then attack the carbonyl of an adjacent molecule, giving you an addition across the adjacent carbonyl. And what that gives us is this fragment here, which has the alcohol on it. And I'm going to circle this fragment in blue. This fragment here is the one that we formed the enolate on. Okay, and we know this because the new carbon bond here is on this alpha carbon going to the carbon that was the carbonyl on the other compound. That's the bond to look for, and you'll know exactly which molecule was the enolate and which was attacked by the enolate. Okay, so in this case, the blue was the enolate, and this one circled on this side in red is the was the carbonyl compound that was attacked by the enolate. And then, of course, to go from the addition to the condensation, we have to remove a small molecule. So just heating like that gives us our conjugated double bond it's conjugated with our carbonyl compound. Okay. So, and just like we learned in chapter 7 when we were making alkenes, if you have an alcohol, you can turn that into an alkene by an E1 or E2 mechanism by either acid or base elimination. Okay, so you eliminate water, you dehydrate with either acid or base. And so it's the same mechanism, but all we're doing is we are kind of making sure it shows up exactly across that alpha and beta carbons, and because it'll be in conjugation with the carbonyl compound. Okay. So questions on the difference between aldol addition and aldol condensation. Okay, because you always have the addition happen first, and you don't always have to do the condensation, which is the making of the double bond. If you want that hydroxyaldehyde or that hydroxy ketone, don't heat it, and it'll stay as that alcohol ketone species. Okay, so now we have another structure here. We have this alpha beta unsaturated ketone or aldehyde. And so we have this conjugated material that we can do additional reactions on, okay? And what we learned about in, let's see, what chapter was that? Our conjugated diene chapter at the beginning of the semester here, we learned that we have different kind of reactions when we have a conjugated diene. We could get that 1,2 addition, or we could get that 1,4 addition. Okay, so when we have this conjugated unsaturated ketone or aldehyde, we can do addition reactions that are similar to that of the dienes we saw. And so let's look into those reactions here. Okay. So once we have this here, we now have an ability of that that conjugated diene to kind of share charge. And we know that the carbon-carbon double bond is typically non-polar unless you have an electronic drawing group on it. But our carbonyl group here is a polar double bond, partially positive to the carbon, partially negative to the oxygen. And so when these are in conjugation with us, we get that charge is spread out and it's a little bit different. The double bond now is slightly more polar than it was before. And we start to see partial positive charge in that what would be the 4 position in our diene, but it happens to be our beta position in our carbonyl conjugated compound, okay? Because remember, we always start with where the carbonyl is And then the first carbon over is our alpha, the second carbon over is our beta, okay? So that being said, our beta carbon is now activated to nucleophilic attack. So if you have something that is negative or partially negative, it's going to be focused on attacking there, okay? But we have to worry about the strength of the nucleophile, okay? The reason is that we still have that partially positive charge on our carbonyl, okay? So now we have a choice, okay? If you have a very strong nucleophile, it's going to favor just attacking the carbonyl and doing that simple addition we learned in our aldehydes and ketone chapter, okay? Because that is the more electropositive carbon. However, if you have weaker nucleophiles that can wait around to go for that weaker carbon, partially positive carbon site on the beta carbon here, then you can actually get addition across, you can get that addition on that beta carbon, which will give you an enol form right here. And then of course that enol form will rearrange possibly, well, it'll be in equilibrium with its keto form. And so we'll end up seeing that that addition of that poor nucleophile happens at that beta carbon, where the addition of the good nucleophile ends up on the carbonyl carbon, okay? So you might think of the a simple addition as our 1,2 addition that we saw in the butadiene, and our conjugate addition, our 1,4 addition for that. But then it rearranges, see where the proton was added up here, but then because of the eno-keto-tautomerization, it moves the proton to here. So technically we did a 1,4 addition, but then rearranged to the more stable form. Okay. Okay, questions on that? This is kind of, I think the analogy to the conjugate addition we did with the 1,2 and 1,4 addition with the alkene, the conjugated alkenes works here because we start with 2 double bonds, and when we do our addition, we'll end up with only 1 double bond in the end. And in both cases, we do this. It's this one you're adding across that carbon-oxygen bond, and the other one you're adding across a carbon-carbon bond, and then rearranging, moving that double bond to this most stable position. Okay, and so the less sterically hindered the carbonyl is, the more likely it is to undergo direct addition, which means aldehydes in particular are susceptible to that direct addition even as the strength of the nucleophile goes down, because it only has that hydrogen blocking that site on the carbonyl carbon. Okay, so let's figure out how we can use this to build new skeletons or new structures on our organic compounds. Okay, so the first way we can think about that is we can say, okay, well, if we attack it with something like a Grignard reaction, okay, remember that Grignard reaction makes that carbon have a negative charge on it, and so that negative charge to carbon is our nucleophile, okay? So, and that tends to be a very strong nucleophile. It's a very small negative charge. It's a very strong nucleophile, and therefore the dominant product we get with a Grignard reaction is the direct addition across the carbonyl, giving us our tertiary alcohol. However, we do see the effect of that conjugation, that partially positive charge on the carbon, because we do get some of the conjugate addition product. But because it's the strong nucleophile, it's going to prefer the direct addition product. Okay. So in the case of things with very strong nucleophiles like hydrides, that H-, and it is a aldehyde, meaning that it is not sterically crowded, we're actually going to see a higher percentage of direct addition on aldehydes than we saw on ketones. And so in this example here, when we react that conjugated aldehyde we actually get almost 100% of the addition happening on the carbonyl. Very little of it happened in the other position. Okay, so that's kind of a demonstration of showing you that the sterics and the fact that we have a strong nucleophile are driving it to that direct addition on the carbonyl. Okay. Now let's take it with and go with a ketone now. So if we have a ketone, we have sterics starting to get in the way here. And even with a strong nucleophile like the hydride, it's no longer favored to do directly across the alcohol. So what we end up seeing is we actually get the conjugate addition, which is the 1,4 addition, so we get the reduction. The first product here, sorry. This first product here is that direct addition across the carbonyl compound, but we can also get the addition across the double bond right here. So we get the addition here, and then the other hydrogen was here, but then through the eno-keto tautomerism, we end up regenerating our carbonyl here. So this is the product of the direct addition. This is the product of the conjugate addition, okay? And then you can take another equivalent of the sodium borohydride and reduce down the last remaining carbonyl, and you're gonna end up with just the cyclohexanol. Notice the sodium borohydride can reduce, well, no, it's gonna, yeah, it's reducing the carbonyl compound directly here after it. So, but this product is, the alkene here does not react to the sodium borohydride because it's not activated to that addition anymore. Okay, so we've demonstrated our compare and contrast between the sterics, how it changes direct addition versus conjugate addition. So aldehydes are more likely to do a direct addition. Ketones are more likely to maybe do a mixture of the two. And the stronger the nucleophile, the more likely it is to do the direct addition. So let's take down the strength of our nucleophile a little bit and look how it changes the product ratios, okay? So when we talked about these organometallic reagents, the Grignard reagents in particular, we also said there was a derivative of them that had copper salts in them. So we had this R2 copper lithium species. And we said that on the range of reactivity, the butyl lithium was more reactive than the Grignard, and the Grignard was more reactive than the copper compound. And I have it labeled here as the Gilman reagent, okay? So lithium reagents are more nucleophilic than the Grignard reagents, which are more nucleophilic than the copper reagents. And it has everything to do with the bond between the lithium and carbon is more polar than the bond between the lithium, the carbon and the magnesium, which is more polar than the bond between the carbon and the copper. So that means that our copper has the least polar bond. That means it's the weakest nucleophile. Okay, so if we compare a reaction with this cyclohexenone right here, we have a double bond in conjugation with our carbonyl. So we have an opportunity for conjugate addition or direct addition. Okay, so in the case of the magnesium reagent right here, the Grignard reagent here, because of the polar bond there, it favors the direct addition across the carbonyl, meaning our double bond is left intact, and we change our ketone to our tertiary alcohol. Okay. However, just by changing the polarity of that carbon metal bond, it's now a softer or less reactive nucleophile, and that less reactive nucleophile has the opportunity to wait around and do the conjugate addition. Okay, so in the case of these organocopper reagents, we're going to see addition here. And remember, the intermediate of this 1,4 addition is the metal salt up here, and our addition of our compound down here with a double bond here. It first forms that enol, okay? And then when you add water to that and break up that metallic complex, it rearranges to the keto form, giving us our final product. So it is a true 1,4 addition when we do the reaction. However, when we look at the thermodynamics of the final product, it actually rearranges to the more thermodynamically stable ketone as opposed to the enol. All right, questions on that? So we have sterics and nucleophilicity. All right, I have a question in the chat here. So basically, the stronger the nucleophile, the higher yield of direct substitution. The weaker the nucleophile, the higher the yield of conjugate addition. That is absolutely correct. Okay, so now if you want to favor one over the other, you can make sure that you have a, you can, for example, react the aldehyde versus the ketone, and you can influence it to be direct substitution, or you use a bulky ketone and you can influence it to be more conjugate addition. Okay, so how can we use this to our advantage? Okay, well, let's look at some other nucleophiles here. Okay, and if we remember back to what nucleophiles were, our strongest nucleophiles were the strongest bases with negative charges, right? So we had our ethene, or ethane, is an sp3 hybridized carbon, and that had a pKa of like 60, okay? So it's a very, very weak acid. So when we made those carbon negative charges, those organometallic compounds with a negative charge on carbon, they became our strongest nucleophiles, our strongest bases. Okay, so as we move down the scale and it gets more and more acidic, as those hydrogens become more and more acidic, they become weaker and weaker bases. So if we look at our next layer of charged species, we go down to our charged oxygen species as our weaker nucleophiles. Okay, then we go down to our neutral species that have lone pairs. Okay, so in the case of our first reaction here, once we go down to having this nice stabilized anion here, that's a fairly acidic proton, which makes it a fairly weak base. We get almost exclusively our 1,4 conjugate addition, which then of course rearranges to give us our ketone. So we get the conjugate addition product, or the addition at the beta carbon here. And we end up with a carbonyl compound. We regenerate our carbonyl compound in the final product. Okay. Now, when we go to this compound here, if it was an anion, you'd have a mixture of products there, but because this is the neutral sulfur species, the lone pair is the attacking species here. That makes it a weak nucleophile, and we get exclusively conjugate addition right here. And likewise, the amine right here is also a weak base. And what we see in this case is we actually have it attacking way over here on our beta carbon, giving us our conjugate addition product. Okay. So before I go any further, I want to draw your attention to something. This conjugate product right here, this starting material right here, was generated by an aldol condensation. Okay. We can make that exact compound by using making the aldol reaction with base and then adding to it to get to this conjugated ketone here. So we can actually use our aldol, our crossed aldol, to get to this as a starting material. Might be in a multi-step synthesis that way. Okay, so weak nucleophiles, we favor that beta addition, okay, that beta addition. Okay, so what if we have other groups there besides aldehydes or ketones? What's going to happen there? Okay, so the idea is that if we have a good leaving group, things that were very reactive in the carboxylic acid derivatives chapter, we actually end up with just getting acyl substitution, because that's the more favored reaction. The acid chloride in this case here is more likely to react with the water or the alcohol here to generate our direct substitution product, okay? And that has everything to do with the idea that those good leaving groups, the chloride ion or the acetate ion, which are very weak bases, would rather just do the substitution reaction and be done. However, as our leaving group increases in basicity, as we get to something like an alkoxide leaving or an amine leaving, we start seeing those being bad leaving groups. And we start seeing, instead of getting the acyl substitution, we actually end up with the major product being our conjugate addition product. Okay, so remember when we were looking at these amide structures here, and we said you can make an amide from an ester because the amine is more basic than the alcohol was, but you can't make an ester from an amide. You can't displace it. Okay, so that same kind of rule applies here, but now that we have this conjugate system here, we're actually going to get that beta addition of our nucleophile onto that product here. And so our amide is going to be much more thermodynamically stable, and so it's going to give us our conjugate addition product because we have a bad leaving group. Okay, now unlike when we had an amide could be made from an ester, in the opportunity where we have a possibility of doing the conjugate addition, alkoxide is still not a very good leaving group. It's still a stronger base than the possibility of using it. So instead, we have the ester. If it's a conjugated ester, we're going to get beta addition. Okay, so if you have a good leaving group like chloride or acetate, you're going to get acyl substitution. If you have a bad leaving group, alkoxide, amine, or even water, the carboxylic acid is OH is a leaving group. Those are very bad leaving groups. Those you're going to see conjugate addition. All right, questions on that? All right, we're at 12:30. We got 10 more minutes to run through this. Okay, so now that we've kind of reminded ourselves of what a 1,4 addition versus 1,2 additions are and how they apply to these conjugated carbonyl compounds, let's do a new reaction with enolates. Okay, so we've done enolates on chapter 18 and the first half of chapter 19. So let's incorporate an enolate into our 1,4 conjugate addition, or our conjugate addition system right here. And we call that reaction the Michael addition. Okay, so in these cases, when we do the Michael addition, we do the first step we do in all of our other enolates is we generate the enolate ion, and that becomes our nucleophile. Okay, so by their nature, the enolates are weakly basic, right? We had to have an acidic proton that we were pulling off so that they could move. So they are weak nucleophiles. If they are weak nucleophiles, that means that in the opportunity you have a conjugated carbonyl compound with an unsaturation, you're going to get primarily beta addition. Okay, so the Michael addition is having an enolate attack at the beta carbon of your conjugated carbonyl compound. Okay, so the general structure there is, of course, our first thing we do is we remove our most acidic proton. And in this case, it's the one in between the two carbonyl compounds. Let me switch colors here. So it's going to happen on this alpha carbon here. It's the one with the two carbonyls, so it's going to be the most acidic. We'll generate our anion, which then is, of course, going to attack at the beta position. And then it'll open up to give us our enol salt. Then our enol salt, once we add water to that, our enol salt will undergo the enol keto tautomerism and regenerate our carbonyl compound. But our new carbon-carbon bond is right here on that alpha carbon of the conjugate addition starting material, but on the beta carbon of the conjugate addition material, but the alpha carbon of the enolate you formed. So you can always track which side was the enolate and which side was the conjugate addition by where that new carbon-carbon bond was. Okay, so we'll see here if your new bond is in 2 carbons over from your carbonyl compound, that's the one that was attacked by the enolate. Of course, it doesn't, you can also see that there's 2 carbonyls here, so that's probably the enolate too. Questions on that? Okay. So enolates are weak nucleophiles, and they react in the conjugate addition version of it, not the direct addition across the carbonyl. Okay, so let's look at that and kind of look at this final product here and think of where the new bond is and what the starting materials probably looked like, okay? So the idea here is that when you're looking at these compounds, you have a couple choices actually right here. You have, let's see, this is an alpha carbon, so that makes this a beta carbon. And this is an alpha carbon, so that's a beta carbon. Ooh, we might be able to make this in two different ways, okay? But let's go ahead and back it up one step and take a look at where we actually are going to start things. Okay, so in this example here, what we're going to do is we're going to end up putting a cyclohexanone, attaching it to something that had a conjugated ketone here. Where's my, well, I'm erasing, that's why, sorry. All right, so we're going to start with this as our system here. Now, another thing to note here is that this ketone right here, these protons here are not very acidic, okay? It's a vinylic hydrogen. Even though it's alpha to a ketone, it's a vinylic hydrogen, which it makes it, brings down the acidity compared with the alpha hydrogen in an sp2 system. So we're actually never going to pull that proton off with this base. So if we look at the other starting material now, we'll see that we have two alpha positions here, but because the compound is symmetrical, it doesn't matter where we take it off this one or this one, it's going to give us the same enolate. So let's first deprotonate and give us our enolate. I'm sorry, our and then our electrons from our double bond will reach out and do this conjugate addition. Remember, our enolates are poor nucleophiles, so they favor that beta addition product. Once we do that, it'll gives us our intermediate salt here. And then once we protonate this, we're going to move these electrons here and give us our final hydrogen at that position. So we can actually look at this and say, okay, in our starting material, we had to have our double bond here, and we had to form our enolate on this alpha carbon. Questions on that? Okay. So the cool thing about the Michael addition is it's kind of, it just like the other enolates, it doesn't have to be a carbonyl, it doesn't have to be an aldehyde or a ketone. It can be other electron withdrawing groups as well, as long as they're in conjugation with your product. Okay, and I apparently showed up on the next slide. So anyway, let's do this one here. So let's do this beta diketone right here. Okay, remember when we do this beta diketone, we're going to end up with a product that is going to have a diketone, and then it's going to be attached with to something else. If we look at this compound here, it has only this vinylic beta hydrogen, alpha hydrogen, so we're not going to make our enolate out of that. If we look at our beta diketone here, we could, whoa, where'd it go? Deprotonate out here, but of course these are our most acidic protons, so we're going to actually form our enolate with that particular here. Now, we do have an aldehyde in our starting material here, so there is a possibility of getting some direct addition. However, because the enolate is a poor nucleophile, the majority of it is going to go to the beta carbon here. So in the case of having a diester, we again are going to deprotonate here in the middle, giving us our enolate here. In this case, we have a methyl group on the end here. So it's going to give us a little bit more sterics, but it still favors the conjugate addition product to give us our, let's see, this is a ketone over here and an ester here and an ester here. Very big structure, but you noticed we made this particular bond here between an alpha carbon on the enolate and the beta carbon on the conjugated unsaturated ketone or aldehyde. Okay. So there's another functional group here that we can use that counts as a conjugated unsaturated material. And that is the use of the cyanide group here, the cyano group. Remember, if we were to draw that out, we have the carbon triple bond to nitrogen here. That carbon triple bond in nitrogen is in conjugation with the alkene, and therefore it's also electronic drawing group. So it satisfies the desire to do that reaction. And because this the cyano group here is in conjugation with that alkene, we will see that beta addition product forming here. So our new carbon-carbon bond is right here between our alpha carbon on our enolate and our beta carbon on that conjugated alkene. Okay, now that's a really complex molecule here, and you can just imagine by going ahead and adding acid and water, we're going to end up with 3 different carbonyl compounds and 3 different carboxylic acids, and that builds a very high level of complexity with a simple single reaction. Questions on that? So cyano groups here are used a lot in these conjugate addition reactions, these Michael addition reactions. Okay. So, and the cyano group here, again, any electronic drawing group will do here. We have, as long as the protons on the substrate are less acidic than the protons on the enolate, you will form the enolate first, and then the enolate will react and give it there. So we can do this with esters, with amides, with cyano groups, and we can even do it with triple bonds. As long as there's an unsaturation, a pi bond in conjugation with a carbonyl or a carbonyl-like species, we can do that addition on that beta carbon. So in this case here, we have our, even though we have acidic protons, they're not as acidic as here. So we're going to get attack of our nucleophile at that beta carbon to yield our final product here. And this particular one is an ester ketone. So it's a beta keto ester. Again, we can have a different electronic drawing group. We have 2 electronic drawing groups on this alpha carbon here. The cyano is one, the ketone is the other. Same thing will happen. We'll form that enolate at that most acidic hydrogen, and then it'll do that conjugate addition on the other substrate. And we extend that even one thing further. We got this beta keto ester again. We're going to deprotonate at this site right here. But now we have 2 choices, 2 double bonds that we can do our addition on. We're only going to do it on one of them. And when we do that, we have to remember we're only using one of the pi bonds. So the other pi bond is still there. And so we have to make sure that we keep track that the other pi bond is still there, and we actually end up with another conjugated alkene with our carbonyl compound. Okay, so if it wasn't so sterically hindered, you might be able to do another addition on there, but I think we have sterics is one out on this one. It won't go through another reaction. All right, question on Michael additions. So Michael additions start looking very, very complex, but always look for that alpha carbon attacking the beta carbon, and you will see that you'll be able to pull the structure out from that. Okay. So just like our enolates are poor nucleophiles, the trapped enol in the enamine is also a weak nucleophile. And so what we'll see whenever we create this intermediate where we take our ketone and react it with our secondary amine to give us our stork-enamine, that stork-enamine reacts as a weak nucleophile, and it will always do the conjugate addition. So we can use that to build up our structures to be, instead of beta ketones, we'll actually end up with lambda ketones, or much longer chains. So let's look at how we do that. Again, once we have this as our intermediate formed just from our amine and our ketone, traps it in this enamine position, the electrons will reach out and do our conjugate addition. Once we get to our intermediate here, we're going to transfer a proton over to this alpha carbon to giving us our final product here. In this case, we started with an aldehyde and we ended with an aldehyde, but now we have to break up that nitrogen compound, and we do that with a little bit of water, a little bit of acid, and that'll regenerate our original ketone from our substrate here. And so we actually are going to end up with this really long aldehyde ketone compound, and then we can use that to do other chemistry. But the key here is that it will always do the conjugate addition because it's a poor nucleophile. Okay, we can take that same kind of concept and do it with the cyanovinyl group right here, this acrylonitrile. Remember, those are also in conjugation, and you'll see the conjugate addition product giving you our extended cyano compound. Questions on that? Okay, weak nucleophiles, conjugate addition is primary product. All right, let me do one more slide and then we'll take a break. Okay. Okay. Just like when we were doing the base choice for our last chapter, when you wanted to form an enolate, the base you choose should be similar to, if you have an ester, you want to use the same base that is your ester. So in this case right here, we have the methyl acetate right here, and so we have the methoxy ester. So whenever we have that methoxy ester, we always want to use the same base that we had. If we have a mixture of methoxy and ethoxy ester, that will keep transesterifying and kind of muddle your final product here. So because you'll form this tetrahedral and it'll just kind of keep switching back and forth. So you want to use the same one that you used in the other ester systems. Okay, so we've talked about how we can do intramolecular aldol condensation and an intramolecular Claisen reaction, and we typically form either a 5 or 6-membered ring here. Okay. Now, in the Robinson annulation, because we're doing this in a stepwise Michael addition and then an aldol condensation, we always form a 6-membered ring. Okay, so the Robinson annulation only forms one type of ring, and that's a 6-membered ring. And it typically regenerates a conjugated ketone. Okay, so let's go through that and see if we can track where all the bonds are going in our system. Okay, so let's start with something simple. This is our ketone right here, our conjugated ketone. And we have our regular ketone over here. So when we do this, we know we're going to make this our enolate because it's not the conjugated species. The conjugated species is going to be attacked by our enolate. Okay, so in the case of this, we're going to use a little bit of base. And what we see, the first thing that's going to happen is we're going to have a formation of our enolate here. Let me erase that ring. And we're gonna form our enolate here, and then that enolate is going to do our beta addition right here to give us our first initial product right here. Notice we still have our ketone intact with our attacking enolate, and we have our ketone intact on the product that was added to our conjugated one. So now, if we didn't have any acidic protons, then the reaction would stop. However, we still have alpha hydrogens here, alpha hydrogens here, alpha hydrogens here, and alpha hydrogens here, okay? So we have an opportunity to deprotonate these things. So what's going to happen is if you, especially if you had an excess of base here, we're going to see that we can do an additional reaction. We can do an aldol addition reaction next. And so we're going to deprotonate at this ketone here. We're going to have that be the nucleophile and do an addition across the carbonyl carbon. And notice that forms a 6-membered ring, okay? And so that makes it easy to form the 6-membered ring, and that gives us our intermediate here. Remember, our aldol gives us our keto alcohol until we add heat. Once we add heat, we get a dehydration, and in this case, it's a base catalyzed dehydration. And the double bond ends up in conjugation with the carbonyl compound. Okay, so we started with a conjugated carbonyl compound. We attacked it with an enolate. We then did additional aldol addition reaction to give us our keto alcohol. And then by eliminating water, we regenerated our conjugated alkene with our carbonyl. So it's all the same steps. We do a Michelson, a Michael addition, we do an aldol addition, and then we do the dehydration to make it our aldol condensation. So all three are the three different reactions from the same chapter. So that's kind of cool. Okay. And because of the way you have to have this addition at this beta carbon, whenever you have that addition of the beta carbon, it sets the stage for only 6-membered rings. Okay, there we go. So the mechanism is just the stepwise mechanism for each of the individual steps. First thing is we form our enolate, okay? Most acidic hydrogen possible is going to generate our enolate. Our enolate is a poor nucleophile, and so it's going to attack at the beta carbon of our conjugated substrate. Once it does that, it of course will rearrange to give us our neutral species, and in this case, it's this species here. Now, if we look at this, we could deprotonate here, but that would give us a 4-membered ring. We could deprotonate here, but that's not going to attack anything. We could, oh, sorry, it's not drying. We could deprotonate here, but that would give us a 4-membered ring. There is no proton here, so we can't do that there. We can deprotonate here, but there's nothing for it to attack. So only the deprotonation at this end is going to give us something that'll give us a 5- or 6-membered ring. And therefore, that's what's going to happen next. We're going to deprotonate at that position right here. So if we look at that step up here, we're deprotonating at the most available position to us. It's the least sterically hindered, and it's one of the more acidic protons we have. Therefore, it will be able to come in and do our nucleophilic attack at the carbonyl carbon. And then through equilibrium, we're going to give us this anion here, which will then, through abstraction of a proton from the solvent, give us our beta hydroxy carbonyl compound. And if we don't heat it, we can stop right here. However, if you heat it, in acid or base, will undergo the dehydration reaction. And in this case, we're showing an E2 elimination. We're showing the base coming in and pulling on the proton first. So it's a bimolecular elimination reaction. These electrons are going to kick in, forming our new double bond. These electrons are going to kick out to regenerate our hydroxide ion. And that's going to give us our final product with our double bond in conjugation with a carbonyl carbon. Okay, questions on the Robinson annulation, okay? Every single step in the mechanism is something we've already done. The key is to keep track of where the carbons are, okay? So the carbonyl on the enolate is going to be the one that gets eliminated. That's going to be the one that turns into the double bond. The carbonyl on the conjugated system is the carbonyl we keep. Okay, so I think I showed that on the next one right here. So that's the key here, is to keep track of what the compound, which compound had the carbonyl on it to begin with, and where it ends up in the final product. Okay, so like I said before, the ketone in the final product right here, this is our final product, had the ketone on the conjugated species. Okay, the ketone or aldehyde on it, the double bond here, sorry, is made from the carbonyl compound on your initial enolate. Okay, so that is the way to look at that. So if that is true, if we try to figure out what, just looking at this thing right here, and we know that, let's change color here, that this right here had to be part of the conjugated addition peak. That means the double bond had to be here. This had to be some kind of carbonyl compound, and it has to be an aldehyde because there's not a methyl group here. And so that breaks it apart for us and tells us that our carbonyl right here had to have this carbon on it, so it has to be a ketone. The other half here had a hydrogen on it, so it had to be an aldehyde. So that breaks it out into our unsaturated ketone here and our aldehyde here. And this is the place where we form our enolate. That's the most acidic proton that we have, and that's the one we're going to pull off to make the problem. Okay, so that is the Robinson annulation. And I'm going to show you, again, another way to track which carbon is which after the break. So I'm going to go ahead and stop sharing and answer questions. Let me go ahead and stop recording.